Okay, 1 second. Okay, welcome to 2182372. Okay, this is section 1. Okay, we have two sections. Okay, this classroom is for section 1. Okay, if you're in the wrong section, maybe you want to switch the room. If you want to switch the section, please talk to IC, and you should switch your registration to the correct section before you come to the appropriate classroom. Okay. This is a core course, right? For your third year. Here is the course description. Let's go over it a little bit. Okay. So as you can see, the course description says Introduction to Telecommunications, Layer Communication Architectures. Okay. So this means the internet protocols. Many of the protocols will be covered in other core courses as well, right? So in particular, we will consider physical layer, okay, a little bit based on transmission medium wire or wireless, right? Medium access control. Network layer, a little bit of mentioning on circuit switching and packet switching, okay? And another important topic for this course is the throughput and delay performance analysis of communication link. Okay. We won't cover the network layer in detail, in particular routing and the other issues related to routing in packet switch networks will be covered in some other courses like NetCentric, right? Nevertheless, we give you some introduction to network topology. The stuff that will be quite unique to this course is the issue related to queuing theory, okay, which is also related to the throughput and delay performance analysis, right? And then for the second half of the course, we give you a lot of overviews and also part of the first half of the course as well. We give you a lot of overviews on different types of telecommunication networks, something like cellular networks, okay, optical networks, internet, of course, and satellite networks, okay. Program learning objectives, course learning objectives are as listed here, okay. You have the schedule for the entire semester as shown here. Okay, as you can see, a significant topic before the midterm will be queuing theory, okay, which is the most theoretical subject of the course, right? Other than that, okay, we have a general introduction to telecommunications, and we will cover the cellular networks and wireless networks in more detail, right? The second half of the course will be overviews on other different type of communication networks, telecommunication networks, okay? So this is a core course. So we have a fixed criteria for the final grade, okay? In terms of contributions to the total scores, right? We will take the attendance, right? Using QR code, okay? There are 2 exams for typical core courses. midterm and final, their contributions are the same. In addition to that, there will be a final project. Okay. Another important assessment is the weekly quizzes, right? So this semester we do it a little different than the previous semester. Okay, we will test you on the lecture material of the prior week. Okay, for example, today I lecture on introduction, right? At the beginning of next lecture, okay, there will be a quiz on today material. Okay, the quiz will start at 1:10. Okay, if you look in the announcement, you can see it. Nice. Offline again, right? So nevertheless, I will. Okay, so I just say it. Okay, so when we have weekly quizzes, it will start at 1:10. Okay, so the first 10 minutes we allow you to check in. Okay, and the quiz will start at 1:10. Okay, and then after the quiz, we continue with the lecture. Okay, and more information about the final project will be coming out as the semester progresses. Okay. Okay. Any question, comments? Okay. Typical core courses, right? So there will be many online quizzes. Okay. And there are multiple choice. So, and you can do it in my course wheel. So each one will contribute only little. Okay. But the point is we want you to have some refreshers every week about the material for the class so that at the time of the exam you get some preparedness already for the paper-based exams. Okay, midterm and finals will be paper-based. Okay, so you do it in the exam rooms. Okay. Okay, so while we waiting for my course view to come back, when my course view comes back, I allow you to check in again. Okay, and if you are not yet in my course view, I will allow you to register. Okay. Okay, for now, let's start the discussion on the first set of slides, which is just an overview. Okay, so let's start on that. Okay, chapter 1 will be a general introduction to telecommunication technologies. Okay. So basically today, okay, we will cover these topics. Okay. I may not have time to speak about all of them in detail. Okay. I, I will leave some for potential self-study, in particular about the history of the internet. Okay. So telecommunication networks are there to used for data communication, right? So basically, data communication is about sharing information, right? Typically, the word tele means remote, right? So when we talk about telecommunication, oftentimes, okay, it's about communication at a large distance, right? Of course, when you exchange information, right, there's a sender or transmitter and there's a receiver, right? So at a granular level, you can think of each data communication as an exchange of information between two devices, right? Sender and receiver. Okay, and of course, if you look at a typical components for a specific data communication, you can break it down into these essential components, right? Of course, there would be a sender and a receiver, right? That are communicating a message, right? And that communication is typically done over a certain transmission medium, right? Depending on a specific communication session we are talking about, okay? We will discuss in much more detail about different transmission medium as the semester progresses, right? So in order for the communication session to be successful, right? Both the sender and the receiver, they have to conform to a certain set of rules, right? To allow them to understand each other, right? And these rules, as you may have heard from the other courses already, these communication rules are called protocols, right? In a general term. Okay, so the picture will look in general like this, right? You have a sender, you have a receiver. Sender is forming a message, right? That will be communicated over a certain transmission medium, right? Based on a strict set of rules, okay, to allow the sender and the receiver to understand each other, right? And as you will see, the transmission medium can be very varying depending on the situation, right? One noted difference across different transmission media, some of them could be wide, right? Some of them could be wireless, right? Of course, if you talk about cellular network, right? Especially for the last hop, right? Going to your mobile phone, the communication has to be done over wireless medium, right? For other type of communication networks, the medium could be wide, okay? So what are these messages that are exchanged in telecommunication networks? So the answer is uh, they could vary very widely, right? Because nowadays with the internet, right, the informations that are exchanged over the internet can have can be very high definition, right? Of course, they could represent complex objects like images, right, or even videos, right? Or it could be very simple messages like text that are exchanged over the network, right? Okay, let's go over some technical discussion about how the information flow, okay, over a particular transmission medium in a communication network. Okay, this is the consideration of data flow over a communication link, right? In the telecommunication jargon, okay, if you consider one specific telecommunication link, right? Between two devices, okay? Sender and receiver. The modes of communication over one link in general could be under three modes, right? Have you heard of all of this? Simplex, half duplex, and full duplex. How are they different? Do you know? Which one is the simplest? Should be simplex, right? Okay, so here is the answer. Okay, so basically, if you consider one particular link, right? And if it so happen that the communication over this link can happen in only one direction, right? Then we call that communication session simplex, right? On the other hand, if the communication can happen in both direction, okay, in other words, the link is reversible, right? Then it could be, we call this session duplex, but there are further classification, right, into half and full. How are they different? Half duplex and full duplex. Uh, can you be more specific? I think you close. Okay. What's so different about walkie-talkie? Some of you may not know what walkie-talkies are. Okay. Okay. Yeah, exactly. So half means that it's not full, right? So in this context, it's a sharing of directions that are not full, in a sense that even though communication can happen in both ways, right? At any particular point in time over this half duplex link or transmission medium, the direction that can happen is only one direction, right? It could be forward or backward, but not simultaneous, right? Like when your friend is talking about walkie-talkie, okay? If one guy is speaking, okay, the other guy will have to listen, right? On the other hand, if the other guy is speaking, you have to listen, right? You cannot talk simultaneously. Whereas the full duplex mode is when both uh, can transmit at the same time. Okay. Clear? Pretty straightforward, right? Maybe test your understanding a little bit. Which of the following communication mode allows for data transmission in only one direction? Which one? Simplex, right? Because even though it's half duplex, communication can happen in both directions. This one, what's the answer? Not simultaneously, but both directions. Half duplex, right? Pretty straightforward. And of course, this one is full duplex. Pretty straightforward. Okay. Okay, next we go to so earlier we talked about only one link, right? But when we talk about networks, typically a network will consist of many links and many communicating parties, right? So let's see. Okay, 1 second. Hmm? Okay, when we talk about network, right? Telecommunication networks, typically we need to consider different criteria, right? Performance, reliability, security, cost, and maintenance. Okay. So if you want to understand telecommunication networks, okay, one way is to classify their physical structures, right? Based on the network topologies. Okay. To this end, okay, you can look at different type of topologies, starting from the simplest to the most complex, right? These are examples of topologies that we will discuss. Start with very simple point-to-point, okay, and then multi-point before progressing to more complicated topologies, okay. So what about point-to-point? It's similar to one link that we talk situation we talk about, right? This is a point-to-point telecommunication network, okay, connecting only two devices, right? And of course, for point-to-point network, as you already saw, right, the communication can be simplex, half duplex, or full duplex, right? Depending on the situation. Okay. Then, okay, for more complicated situation, even though there's one link, right? When we go beyond point to multi-point, there could be more than two devices, right, that are sharing this communication link. Okay. So in this situation, we call this type of network topology a multi-point network. Okay. This could still be in one direction or bi-direction, right? So let's assume it's bi-direction, okay? Then it could still be either full duplex or half duplex as well. But if it's bi-directional, it means that any devices can use this link to communicate with the other devices sharing the same link, right? Like, for example, this guy can send to this guy, right? Similarly, it can send to this guy and this guy. And similarly, for these three guys, they can communicate with one another and to this mainframe as well. Okay. So that's network topology consisting of only one link, but the difference is the point-to-point topology consists only of two devices, right? Multi-point, there could be many more. Okay. This one, what is so special about this topology? How many devices are there? 5. How many links are there? How many links are there? This one is called mesh. Just count, right? It says here 10 links. What is special about the number 10? Okay. Yeah, 5 choose 2, right? So it means all pairs of devices in the network are connected directly, right? This is what we call mesh topology, okay? Or fully connected network, right? Pick any pair of devices, there would be a direct link between them, okay? If we missing any direct link, then we will not call it a mesh, okay? A mesh is a fully connected network only, okay? What about this one? This one is called a star or hub topology, right? Which device is a hub? This orange device, right? Because it's the central device for this network, right? So if you look at this, okay, the communication messages um, across any other devices other than the hub, we have to pass through the hub, right? So that's why we call it a hub. Okay. Sometimes we call it a star topology as well. And it makes sense, right? Even though here um, we didn't move it in the form of a star. Okay, it's clear that the hub will act as the center of the star, right? If you move the links appropriately. Okay. Okay, many of you may be familiar with the next topology. This, if you are well versed in computer architecture, right? What is this topology called? Similar to multi-point topology we discussed earlier, right? So basically, this single share link is called a bus, right? Of course, this is a multi-point network, right? With one long communication, telecommunication medium that acts as a backbone to the link, to link all devices in the network, right? So typically in bus topology, the devices are connected to the bus cable by devices called drop lines shown in green, or taps. Okay, drop line and taps. Okay, before connecting to the bus, right? Pretty straightforward, right? For the introduction. Next topology, more complicated. Okay, is like bus topology, right? But we wrap the bus around, right? So here, when we talk about this ring technology, okay, it means that the bus of the network is circular, right? It's wrapped around into the form of a ring. So the signal is passed along this ring, okay, typically in one direction, okay. In more complicated situation, the ring could be bidirectional, but typically in that case, we will draw two rings, right? One in each direction. So let's say it's a ring in one direction, right? Then by wrapping it around, it means that all devices, all pair of devices can communicate uh, with each other, right? Over the ring, right? Let's say the ring is clockwise, right? Then if this guy want to communicate with this guy, right? Then the message will go in that direction. Okay. Okay. And similarly, all pair of devices over this ring can communicate, right? Any question? Pretty straightforward, right? Again, let's test your understanding a little bit. Okay, not yet. Maybe more complicated topology is a tree, right? And of course, in the situation where you consider a larger network, right? It can consist of the topology that is hybrid, right? So in this picture, you can see, okay, you have a network of sub-networks, right? Each of which conforms to different topology, a different topology, right? Like this one is a ring, whereas these three are star topologies, right? Yes. That's what I said, right? So typically, 1 second. You mean these two? Uh, which line again? From where to where? No, we will not call ring. Yeah, it would be some mesh has to be fully connected. Yeah. Okay. It will be a hybrid. Yeah. So here, right? You have to specify the direction of the ring. Clockwise or counterclockwise, and you have to conform to that. Okay. Good. Yeah, it has to be fully connected. Yeah. So it's like a bus, right? Except that the bus is circular. Yeah. Okay, good. Let's test your understanding a little bit. Okay. Star, right? Okay. Pretty straightforward. This one, every other device at the keyword, right? Fully connected. So it's a mesh, right? What about this one? A, B, C, D, can you say? D, right? Because all devices share a single link, right? So if many devices are communicated simultaneously, okay, the performance can decrease significantly, right? Of course, A is wrong, right? Because we save a lot of cabling because everyone share the same cable, right? Also, it will make the network not too difficult to troubleshoot because all the fault will be concentrated only through one link, right? Yeah. And of course, there's no central hub like the star topology. Okay, clear? Okay, this one I would say is a bit fuzzy. Okay, what do you think? So let's say there are n devices in the ring topology. How many links are there? You can go back to the picture. How many devices are here? 1, 2, 3, 4, 5, 6. How many links? The number of links is equal to the number of devices, right? What if one link fails? Pardon? No, link. This is what I mean by failing. So what if yeah, 1 second. Where is it? Yeah, this one. What happened is one connection fail, one link fails. What do you think will happen? I would say it depends, right? On which pair you're talking about. So like say if the top link fail here, okay, and if the orientation is happen to be clockwise, right? So it means that if this link fail, this guy cannot communicate with that guy for sure, right? But this guy can still communicate with the rest of the devices. I would say it's pretty gray in this case, but it depends. The network may be configured in such a way that, okay, if it's not, if the ring fail, okay, then all the communication will be disrupted. Yeah. So I'm asking you if a link fail. not two devices. Okay, devices will not fail in this question. Okay, there are 6 links, right? The question is, what if a link fails? Then what will happen? Yeah, one. So that's the example I gave. Let's say the top link fails here. Okay, if communication happens to be clockwise, right? Then this guy will not be able to communicate with that guy, right? In particular, this guy will not be able to communicate with any other guys, but this guy can still communicate, right? Because the communication will go over all the other links other than the failed link. Yeah, let's say this one fails, right? This guy can still reach this guy, this guy, this guy, and that guy, right? But on the other hand, this guy, this link fails, he cannot reach any other guy, right? So it's a bit gray. So I would say none of the answers are entirely correct. Okay. What about this one? Which topology is very reliable and fault tolerant? Okay, I would say, okay, here mesh here with the caveat, right? That um, all the links should be at least half or full duplex, right? Because because it's fully connected, right? If one link fail, you can route the traffic through some other links. Okay, good. Okay, this is pretty straightforward. Bus, right? I would say um if there's a ring topology in the choice, you can choose that as well, right? The bus is still single. Yeah, but as I said, you can think of a ring as a bus wrap around, right? So yes. Okay, what's the key advantage of the star topology? I would say C, right? Because if you want to extend it, you know how to do it, right? You don't have to figure out how you should wire the next cable, right? You want to extend, just directly connect the new guy to the hub. Okay, this is pretty straightforward ring, right? Uh, 1 second. Okay, in some literature, you may have heard of the word unicast, broadcast, and multicast, right? Do you know what they mean? Unicast mean unicast is like simplex, right? Broadcast, of course, is communication. It's like communication from a hub, right, to all other devices. Whereas multicast is communication from one device, not to all other devices, but maybe some group of them. Okay. Just to let you understand the jargon a little bit, because different literatures, they use different jargons. Okay. You just need to understand them at the conceptual level. Okay. Okay. So next is about network type. So here, when we talk about network type, okay, we classify them according to slightly different criteria based on size, geographical coverage, and ownership, right? Have you heard of LAN, local area networks, right? What is the keyword here among the three words? Local area network. Area, it could be small area or large area, right? But I would argue the keyword is local, right? So it means that the entire network belongs to a single owner, right? Something like if you connect multiple devices in your office, right? And the keyword local also signify that this small network, it doesn't connect to a wider network, right? You will contrast LAN with types of network called another type of network called wide area networks, right? So here for LAN, typically it's a network that is privately owned, okay? And it connects some devices basically in well-defined or smaller area, okay? And different devices are defined by suitable addresses, okay? Depending on the situation, could be MAC addresses if it's not connected to a wider network. In more general situation where the LAN is connected to a wider network, you could use globally identified addresses like IP addresses. Okay. So here is a simple picture of local area network, right? You can see the evolution. Okay. The top picture is like the first generation of local area network, which conforms to what type of topology? Top picture, what topology that we already discussed? It's written here, right? It share a bus, right? So this in this bus topology, okay, all the devices in a LAN are connected through the bus, right? And of course, you already know that this can lead to low efficiency, right? When many devices simultaneously talk to one another, right? Thereby consuming, thereby sharing significant capacity of the bus, right? So in next generation of LAN, okay, typically a smart switch is employed, right? And this switch conforms to what type of topology? Star or hub, right? So this switch is acting like a hub. So now the links are no longer shared, right? Even though the switch is shared, okay, its role is only to relay messages, right? So it doesn't lead to so much drop in efficiency, especially for high quality switch, right? They can handle a lot of forwarding of messages. Okay. Any question, comments? Okay, let's test your understanding a little bit. What do you think is correct? Sorry? B? Okay, because A is large, right? That's wide area network, right? And C, satellite, no, right? Satellite communications are wireless, right? So when we talk about LAN, typically it is a wide network, right? multiple LANs connect to each other, that's definitely the next one we talk about. That is wide area network, right? Okay, this one may be on the topic that I didn't cover specifically in the slide. Do you know what type of cables are used for typical LAN networks? Ethernet, right? Or you may have heard it as, what's the other name for Ethernet cable? I don't know. Some people call it RJ45, right? Or, okay. So basically, it's the medium is electrical, right? Whereas fiber optic cables are, the medium is light, right? Cellular, of course, is wireless, right? It's not even wide, and similarly to satellite. Right? Yeah. Okay, the A and C are wireless, right? B and D are wide, but the carrier is different, right? Fiber optic, the information is modulated into the light wave, right? Whereas Ethernet is a copper wire, right? So it's just use electrical signal. What about this one? C. Yeah, because it's wide, right? Yeah, exactly. Okay, and typically the bandwidth is much larger than wireless networks, right? And the latency is lower, okay, because it's wide. Okay, contrasted this to larger network called wide area, right? Again, the keyword here is wide, okay? And the way you should think about it is wide is when you want to connect many LANs together, right? To allow different LANs to talk to one another, okay? That is the typical situation when of wide area networks, right? So if you talk about a local network, typically limited in size, but if you connect many of them, okay, the entire network will cover wider area, right? So how are you typically connecting different LANs together? So in a nutshell, through suitable connecting devices, right? The connection could be through a single link like that, okay, where one connecting device is to connect one LAN, the other connecting device is to connect to the other LAN. Or the connection could be configured in a more complicated fashion. This is called a switch WAN, right? With basically this connecting devices, the set of connecting devices are arranged in the form of a ring, right? And then these four devices can connect to suitable LANs, okay? Okay, this is a typical situation using this point-to-point connection between two LANs, right? You see, on the left, you see one LAN. On the right, you see another LAN, and you want to connect them together. Typically, the connecting devices are routers, right? That are directly connected to each other, okay? What's the difference between the end devices like laptops and the intermediate devices that are not at the edge of the network here. Do you know the differences? In this simple picture of a WAN, how are the routers different from the laptops? And also the two switches here. Which devices are generating and consuming messages and which devices aren't? Only the end devices, right, would generate or consume messages because they are the final destination or the source of the messages, right? The connecting devices, their roles are only to relay messages, right? They do not generate or consume any message. Okay. If you want to connect more and more LANs together, okay, the picture can get complicated quite quickly. So as you can see, how many LANs are here in this picture? How many LANs are here? How many LANs? For which one? Which obviously the bottom two yellow are two LANs, right? What are the other two? Three, right? One, two, and then this small one, right? This one is so first of all, okay, there's like a hub of connecting devices in the form of a switch WAN connecting these three LANs. On top of that, okay, there are three point-to-point WANs that enable the connections, right? Okay, what do you think is the answer of this? What should be the answer? B, right? A is wrong because of the word small, right? Yeah, B, right? B is correct. What about C? Bluetooth is wireless, right? No. WAN is typically Y as well. Yeah. The backbone is definitely Y, right? Yeah. That's, you can think of it like that. Even though when in general when we talk about a general WAN, right? There could be part of the constituent LAN that is partly wireless, like here. So here, right? So here, right? In this picture, the entire thing is a WAN, right? But if I look at this residential LAN, yeah, could be that I could install the wireless router as well, right? So only this part is wireless, but the backbone of the WAN is still mostly wired, right? Okay, switching. Okay, I think you are all familiar with this topic already. Do you know the difference between circuit and packet switch networks? Has it been covered in some other courses already? Circuit switch network. Do you know the difference? Do you want me to review it? Sorry, you still right? 1 second. This is okay. So typically, when we talk about large network, right, consisting of many devices, right? there would be many switches that are employed, right? And these switches are there, switches and routers are there to forward messages, right? As I already mentioned, these connecting devices like switches and routers, they do not generate or consume messages. They are there to forward, right? Messages. What's the difference between a switch and a router? Which one is simpler, switch or router? They are both for forwarding, right? But switch is simpler because for a switch, okay, typically the direction for each message to forward is fixed. The switch does not need to make a routing decision, okay? Hence the word switch, not route, right? A router, typically when there's an incoming message, the router has to decide in which direction to forward that incoming message, okay? But they are both for forwarding, okay? And for general telecommunication networks, okay, there are two primary ways of doing switching. One is called circuit switch, and the other one is called packet switch, right? To explain the idea in more detail, I would urge you to consider this simple toy network, okay? This one, okay, you have how many devices? 8, right? With 2 switches, okay? And a dedicated connection here, okay? Through basically the backbone bus, right? And the idea is that this backbone bus connecting the 2 switches will allow the devices on the left to talk to devices on the right and vice versa, right? So in this context, you can do switching in 2 ways. You can do circuit switching or packet switching. How do you notice the difference in, so this is circuit switching, this is circuit switching, this is packet switching. What difference would you notice? Which element is not there in circuit switching? The queues, right? The queues are not there for circuit switching because in circuit switching, okay, for any communication session, then the network will assign a dedicated connection called a circuit that is always available between the sender and the receiver, okay? So what does that mean? How many sessions can happen simultaneously here? Remember, so I only assume that the guy on the left will talk to the guy on the right, right? And vice versa. I will, in this topology, I will not allow the guys on the same side to talk to one another, okay? So that means how many sessions can happen simultaneously? 4, right? So in circuit switching, the network is provisioned in a sense that, okay, let's say this bandwidth is 100, right? Then each maximum, each possible circuit is assigned only the capacity of 25 megabit per second to allow them to be always available, right? Even if all the 4 circuits happen simultaneously, they can still share the high bandwidth link, right? So that's circuit switching. You provision all possible fixed circuits so that they can happen simultaneously at all time. And that is different from packet switching, right? Because packet switching is much more opportunistic, right? There is no provision. There's no provision for, first of all, there is no fixed circuit being assigned, right? If you talk about a particular communication session, the bandwidth will not be limited, right? The bandwidth could depend on how congested the network is. Okay. So in this case, for example, in this simple network, right? This link could be of a lower capacity, okay, and it could happen in packet switching that if all of them, all of the four guys on the left talk simultaneously, okay, and with high bandwidth, again, there's no provision, right? You cannot limit their maximum capacity. If they simultaneously talk and they send at high bandwidth, right? It could happen that the network is congested. And in that case, what would happen when there's a congestion in the network? What would happen? The information could be lost, right? And that loss is happening through the queues, right? Because as you can see here, messages are queued up, right? In the two queues. If I'm sending more than I can consume, right? What would happen? It's like a water pipe, right? If I pushing in too much water before I drain it out, what would happen? Some water will be spilled, right? So in this case, messages could be dropped, right? And or could be lost, right? And if you want to correct for that type of error, you need extra mechanism like retransmission through the feedback between the receiver and the sender to enable that retransmission. Okay. So in a way, okay, circuit switching is kind of like a provision network, right? Where you assign at the outset uh, how much capacity each circuit can occupy, right? And then you decide the network for the worst case scenario, right? For the case where all circuits are happening simultaneously, the network should still be function, right? Whereas for the circuit switch, for the packet switch network, okay, you cannot guarantee the worst case, but what you can do is you design it for the average case, right? You design so that with high probability, if the network is not too congested, most communication will go through, okay? But because of the nature of not provisioning all the session at the outset, there could be some unfortunate cases where congestion could build up, right? In some case, in those cases, there will be some loss. And in packet switching network, the network will correct for the loss to some extra mechanism, okay? Yeah, so in circuit switch, there will be no loss because you already provisioned for the worst case. In packet switching, you design for the average case. In the worst case, where bad thing happen, you cannot guarantee 100% reliability, but you can have extra mechanism to provide delay reliability by retransmission. Okay. Yes. Uh-huh. No, router is often wide too, but router is different in a sense that, as I already mentioned, right? The word route means you have to make a decision about the direction. Okay, so it means for each incoming packet, right? There may be many outgoing links. A router will have to decide which outgoing link to forward the message. A switch will just forward it fixed, okay, to a fixed direction. So it's very different. Actually, just bandwidth control of the data. I guess it is preferred like share smaller piece of data. You can also argue that on average case, packet switching is often better because circuit switching you have to provision for the worst case, right? But that worst case may happen with very low probability. Yeah. Yeah. Something like that. For most average case, packet switching would perform better. Like something like the internet is packet switching networks, right? I think it's used for system that will always guarantee reliability. Like, if you talk about telephone network, right, land phone, it will never fail, right? And when you call somebody over a telephone network, once they answer, you can communicate right away. But imagine how what's the difference to that to email, right? When you send an email, yeah, there will be delay, and the delay could be very wide ranging, right? Sometimes, yeah, exactly, yeah. So that depends on how congested the network is. Yeah. Yes. But packet switching is designed to use the capacity of the network more efficiently because you don't provision for the worst case, right? The worst case may happen with very low probability. So oftentimes you want to use the network at its full capacity. Um, at some unfortunate cases, there will be some losses, but the internet, for example, they have mechanism to compensate for the loss, like retransmission. If you heard of the TCP protocols, right? You may have known that that is used over the internet, right? You may know that it allows for loss, right? When network is very congested, but there is a feedback mechanism in the protocol to know which packets are lost and retransmit at a later time appropriately. Yeah, it could be very if the network is congested. Yeah. Yeah, just look at your email. Like sometimes just send the email to yourself, right? And measure the time difference between the sending time and the receiving time. You can see it's very wide ranging. Yeah, your question. Pardon? Uh yeah, if you fix the same pair of sender and receiver, I would say it's the same, but the difference is the performance. Okay. Yeah. Yeah. Uh-huh. No. It's not one at a time. Circuit switching, okay. As I said here in this toy network, right? Only guy from the left would talk to guy from the right and vice versa, right? But they can still talk simultaneously. Like all four of them can talk to the guys on the other side, right? So in this case, the maximum bandwidth for each of these four circuits would have to be provisioned in a sense that there's some would not exceed the capacity of the main link. So all circuits can happen simultaneously. The other one is not provision. It happened opportunistically because, for example, the capacity at the bus link can be fixed, right? But the rate at which all these guys are sending are not controlled, unlike the circuit. They can send as much as they want. And if they are in the rare situation where they send at maximum rate, maybe the network will be congested and some messages will be lost. But the idea is that on the average case, if you design well for using the average data rate, right, then most communication would go through. Okay. On the other hand, if you look at circuit switching, okay, let's say you can think of it in terms of probability, right? So let's say each guy is transmitting, each guy on the left is transmitting with probability 10%, right? Oftentimes they are silent, right? So then what's the probability that all of them will talk simultaneously? It's only 0.01%, right? So then that means at almost 99.99%, the calling will not be fully utilized, right? So in those high probability event, you won't be using up the link, okay? But circuit switch will not allow you to communicate at all, okay? Okay, thanks. Okay, so we've gone 1.5. Do you need a break or you want to continue? Okay, maybe finish this quiz before having a small break. Pardon? That can be self-study. Yeah. Pardon? Could be. Yeah. Okay. Let's see. Okay. What about this problem? What do you think is the correct answer? Yeah, any of you? See? Because forwarding, right? That's the keyword for switching. What about this one? This one? Because yeah, LAN and internet, right, is based on the concept of packet switching, because you want to use the network as much as possible, okay? And then if there's congestion, then you fix it up later using a retransmission mechanism, okay? There are other type of networks, but the global ones are telephone networks, okay? I mean, the old telephone network, okay? Nowadays, we talk about cellular networks, right? That are connected to the internet as well. Yeah. Yeah, landline, yeah. And also telegraph networks, but you don't use it anymore. Yeah. Okay. So next one is, okay, let's finish this one before we have a break, maybe. Internet, you all know what it is, right? So I go over it very quickly. So basically, we talk about LAN and WAN, right? The best way to think about the internet is that it is a global WAN network, right? So the general picture looks like this. So it's a wide network, wide area network, right? Connecting all the devices globally, right? And so you can see it's the structure of the core of the internet is hierarchical, right? So you have several local networks, right, that are connected to the suitable provider networks, right? This could be providers of your smartphone subscription or fixed wireless subscription, right? Yeah. So like here, if you use a cellular network, right, this could be the operator to which you subscribe, like through AIS, right? Or if you use the Y internet, right, could be the fiber cable internet subscriber that you use, right? And then because the network is global, all of this, they have to be connected to the backbone of the internet, right? So the backbone will consist of dedicated infrastructure devices owned by these provider networks to connect all of them together, okay? And depending on specific regions and alliance of different provider networks, okay, some some of the provider network may allow for direct connection among them, right, through peering points, okay. I don't want to go into too much detail on the internet itself because there will be other courses that will cover it in much more detail, like net-centric. Okay, but basically the way you access internet is basically through these provider networks, right? You may have heard of them as internet service provider or cellular provider, right? Depending on you using a wire connection or wireless connection, right? We will talk more about the cellular networks and how it is connected to the internet as well for the next topic. Okay, any question, comments? Okay, if there is none, okay, let's maybe have a small break, okay, maybe 10, 15 minutes so that I can allow those of you who have not registered in my course view to register and allow you to be able to check in again is if course view is coming back up, okay. Okay. Remember, use this section of my course view, this session of my course view only combining the two sections, right? Some of you may got invited into the other course view session dedicated to section 1, but we will use this one instead, combining the two sections. Yes. Yeah. One second. Yeah, I will show the code. Okay, don't use this one. Use this combined one. Okay. Okay, first of all, let me open the check-in page again. Okay, let me open the registration page first. Okay, if you have not registered, please do so using this password. Okay, please request to join using this password. We should have most of you already because I see more than 100 in the roster. But if you're not in here yet, if you don't see this session in my course view, notice that it's for both sections, not only for section 1. Okay. If you don't see this session in my course view, please request to join using this password. And then I will allow you to check in again. Here. Okay. Okay, please check in. Okay, since we have some time here, let us talk about the history a little bit, okay, of the internet, right? So I mentioned earlier about LAN telephone networks, right? Before the internet, the important global networks were telegraph and telephone networks that are circuit switching networks, right? And as I already mentioned, right, because for circuit switch networks, you provision for the worst case, right? So that means those all networks are suitable for constant rate communication, okay, at all time, okay. And those networks are provisioned only for the worst case scenario, right? Okay. Yeah, since some of you complain, I can talk about it a little bit, okay? Okay, but back then, okay, there was a emerging need to construct a global network for bursty data communication, okay? Sustaining communication of variable rates at different times, right? So that's why the internet was born based on a different concept of switching that we already discussed called packet switching, right? Okay, sorry, I didn't switch the slide. Okay. So in order to make the packet switching work, right, you need to come up with important protocols to allow for packet switching at the global scale, right? And that was the key to the invention of the internet. And that is the creation of this transport control protocol, okay, for packet switching, okay, to allow the internet to service variable rate traffics at the best effort, right? Using the concept of packet switching instead of circuit switching. Okay, at the beginning, when you talk about internet, right? Because it's packet switching, you cannot guarantee perfect reliability on the worst case, right? So as a consequence, at the beginning, there were some applications that was not suitable for the internet, something like voice communication, right? Because the delay requirement for voice communication is very, very stringent, right? Because if there's too much delay, the recipient wouldn't be able to understand the talker, right? But nowadays, because of the improved technologies, the internet has become much better. Okay. Nowadays, I would argue that the internet could support all sort of applications because the TCP protocols also allow for perfect reliability through the external feedback loop for retransmission, right? So nowadays, you see almost all application can be supported over the internet, right? And I would say the ancient circuit switch networks like landline telephone have become obsolete. Okay. Okay, let's go over the final topic before uh, uh, we go back to the syllabus a little bit before we dismiss the class today. Okay. So we talked about protocols earlier, right? Whenever we talk about communication networks, right? The communication has to be done over fixed rules, right? For the internet, these rules are called protocols and they are public, right? Because all the protocols that are used over the internet, okay, are supposed to be known by all the communicating parties. That's why all these protocols are standardized, okay? And as a consequence, this standardization have to be done by some organizations, right? So let's look at the normal process of how you can standardize an internet protocol, right? So basically, there's a strict procedure for which specification attains the internet standards status, okay? That begins with basically an internet draft, right? Proposed by relevant organization, right? The typical route for escalating the standardization is to go from a draft to a proposed standard, right? And then this proposed standard would have to be tested, right? Through certain trials, okay? Before it can be evaluated and approved to become a draft standard and a subsequent internet standard, okay? So protocols come and go, right? Some protocols become obsolete over time. Its status may be de-escalated into historic standards when some other protocols replace them, right? There are some special drafts, okay, that are not widely used. Some of them could be experimental for research purposes, or some of them would be would serve as tutorial draft for relevant parties. Okay. Okay, I will close the lecture with the governing bodies, okay, related to the internet standard, right? Many of you may have heard of this organization. ISOC stand for Internet the Internet Society, right? Okay. Under ISOC is the Internet Architecture Board, IAB, okay, which is organized into two different task force, right? IR stand for Internet Research. IE stand for Internet Engineering, right? So basically, the right organization is for day-to-day operation of the Internet, whereas the left one is for more experimental and research purposes, right? Different standard drafts are organized into different working groups or research groups, depending on the topic, right? And each of them will handle the process of standardization of different drafts according to this process that I already mentioned, right? Before any standard, any draft can be standardized, okay? Suitable tries have to be performed and evaluated before the standard can be escalated into the subsequent level until it is formalized into the internet standard, okay? The final internet standards are published over the internet, right? Some of you may have heard of the documents formalizing this internet standards. They are called requests for comments, right? RFCs, okay? Different RFCs will explain the detail of different internet standards, okay? And they are published by this relevant organization over the internet, okay? So everyone can have access to the protocol so that they can use the protocols to communicate over the internet. Okay, that will conclude my discussion for the introductory topic. So let's see. So the slides are published in my course view, right? Again, I stress that we will share only this session for my course view for both sections. So make sure you have access to this one. Okay. Before I dismiss you for today, I just stress that the material that I lecture today will be for the quiz next week, starting at 1:10. Okay. And then we go on next week on the next topic, right? Of wireless and mobile cellular networks. Okay, for this section, okay, the lecture will be Zoom casted, okay, using this Zoom link, okay, and the password is published here. Okay, before we dismiss you for today, let me close by showing you the syllabus again, because at the beginning there was a problem with my course view, right? So here you can see more information about the course. You can see the detail of the course description, program learning outcomes, and course learning objectives or outcomes. Also, you can see the schedule for the entire semester. Okay. The criteria for the final letter grade is fixed like this. And for this semester, we have 2 exams, which are paper exams, midterm and final, like the other core courses, and also a final project. Okay. There would be many weekly online quizzes in my course view. Online quizzes. I haven't decided, but it's very hard to make it close book. Let's see. I'll let you know next week. Okay. Quizzes will be based on the material you learn in the class in the prior week, right? And the online quizzes will be at the beginning of each of the classes. So there'll be many of them, but because it's online, okay, we will not weigh it too much, okay. In total, it's only 10%, just to keep you ready and in pace with the material in the class, okay. And we do the attendance check by QR code, okay. Definitely for the first 10 minutes, but maybe for some special week, we allow for more time. Like today, there's a problem with my course view, right? So I allow you to check in after 10 minutes past 1 p.m. as well. Okay, any question, comments? Okay, again, the lecture slides will be posted here. Okay. This one, I think is redundant. Okay, we can delete it because it's already in the syllabus already. But we keep it anyway. The recording for this session will be available from here, right? Like in the other courses. It will take some time for Zoom to process the recording, but when it's ready, you can access the recording from here.